I'd like to welcome you to section 2.2, talking about the flow of energy in an ecosystem. During this unit, during this section, we are going to be talking about how the flow of energy, how energy flows throughout an ecosystem. We're going to identify the ultimate source of energy for photosynthetic producers, and then we're also going to describe the difference between food chains, food webs, and look at our different pyramid models. So the first thing that we have to realize is that all organisms do need energy. Our energy comes from the food that we eat, and that we are an animal and that we eat other things. The ultimate source of all energy, though, does come from the sun through photosynthesis. So when we talk about the flow of energy, we have a couple of big categories that we can look at. And the first one are our producers. Now, producers, just like it implies, produce the energy. These organisms use energy from the sun or energy that is stored in chemical compounds to make our food. So here we're going to see our organisms that do photosynthesis or organisms that do chemosynthesis, taking the sun's energy and turning it into food. Producers are also called autotroph. Auto meaning self, troph meaning to make food, and so these organisms make their own food. The other group of organisms that we have are consumers. Now, consumers, just like the word says, are going to consume food from other organisms. These organisms depend on others for their source of energy. They have to eat their food. These consumers can also are also called heterotrophs. Hetero meaning different. So these organisms get their food or their energy from other organisms. They are not self-made. And we're going to be talking about 4 different kinds of heterotrophs. Now, when we talk about our different heterotrophs, a lot of these words that you're going to have end in vor, V-O-R-E. Vor is a suffix that comes from the Latin word vora, meaning to eat. And so it's going to let you see how these other organisms eat their food. So the first type of heterotroph that we're going to talk about are herbivores. Now herbivores, herb is plant, vor meaning to eat. So these are going to depend on other autotrophs for energy. Anything that eats plants for their energy source are herbivores. Okay, so grazing, any seed-eating animals like rabbits, cows. Then we have a carnivore. Carn means meat, vor meaning to eat, and so carnivores are organisms that eat meat for their energy source. They are going to be eating other heterotrophs. Okay, these guys are usually top of the food chain. Okay, these are the top ones. Not too many people are eating other carnivores. And there's a picture of our herbivore. So we have herbivore and carnivore. The third vor that we're going to talk about are omnivores. Okay, omnivores are going to be eating both herbivores and carnivores, so they eat plants and animals. The most common omnivore that we're familiar with are humans. Raccoons, bears, and mockingbirds also fit into this category as being an omnivore, that we get our energy from both plant and animal. Now, if you're a human and you happen to be a vegetarian, that does not make you a herbivore. We are still, as a species, considered omnivores. And the last one that we're going to talk about are detrivores. Now, detrivores are also called scavengers, and they are going to eat dead things. They are not decomposers. These are scavengers. These are the buzzards and the beetles and stuff that are on the side of the road that break down, that they actually get their energy from dead things. Now, the third category that we can have, so autotroph, heterotroph, the third category that we can have are called decomposers. Now, decomposers are a little bit different from detrivores. And I apologize, we do not have a slide for this one. Decomposers are organisms that are going to break down the substance and return those nutrients back to the soil. So if you drive by and there's roadkill with a crow or a buzzard or something a vulture eating it, that would be a scavenger. Then whatever's left, then the worms and the bugs will come in and they will actually break down the rest of that organism and put that carbon and that nitrogen back into the soil, and that would be the decomposer. So we have autotrophs who make food, we have heterotrophs who eat other things, and we have the decomposers that are going to kind of put the building blocks of organisms back into the soil so that they can be reused. Now, since we know about all the different organisms, we can talk about how energy flows between those organisms in the ecosystem. And ecologists use 3 different models that we're going to talk about. The first one that we're going to talk about is a food chain, and I know people have heard about food chains and you've studied it when you've studied ecology before. Now, food chain is a very simple way of showing how matter and energy move through an ecosystem. There's usually only 3 to 5 links in a food chain. As you move through and that energy moves, organisms lose it. They have to reproduce, they have to live. And so as you move down, the amount of energy that you actually receive from that organism is less and less. And so we only like to see 3 to 5 links in our food chain, just because by the time you get to the end, if you have more than 5, you're eating so much that you won't be able to keep up because of the decreased amount of energy that you would be getting. Like I said, the energy, the reason why we don't have those 5 links, and notice up on our screen we have algae that gets eaten by the fish, that gets eaten by the heron, that would be considered 3 links in our chain, because that energy gets lost. We have movement, we have to be able to produce heat if you're an animal. We have to reproduce, we have to care for young, we have to find mates, and all of that requires energy, and so we lose it as we move on. And a good rule of thumb is that you lose roughly 90% of your energy as you move to the next link in the chain. So 10% moves on. So if we start off with 100% of the energy available in our algae, only 10% of that is moving on to the fish. So the fish is going to have to eat a lot of algae to get back up to its 100%. And then when we move from fish to heron, we lose another 10%, or we lose another 90%. Sorry, I was interrupted. So, like I was saying, algae moving on to fish. If the algae start out at 100%, then only 10% of that will move on to the fish. So the fish have to eat a lot of algae to get enough energy in order to survive. And then, let me fix this for you. And then, there we go. 10% then gets moved on from the fish to the heron. So of the original 100%, only about 1% of that energy is actually getting moved on to the heron. Each organism is considered a trophic level. Now, one thing about food chains is that they only show us one way that it can be. Now, in reality, many different species are going to occupy their trophic the same trophic level. And each organism isn't stuck in our trophic level. So if we would look at humans, if I'm eating a cheeseburger, okay, if I have lettuce and tomato and I'm eating that, that puts me on a very different trophic level than when I'm eating the actual hamburger itself, because it has changed which step I'm at in that food chain. Here's an example food chain. So we start off with grass. Remember, that is the sun is the ultimate source of energy for our food chains and our food webs. Grass is our producer, or our autotroph. It is going to be eaten by the grasshopper, which is going to be called our primary consumer. It is the first organism doing the consuming. That's followed up by our secondary consumer, our snake, followed by our tertiary consumer, the hawk. Then when the hawk dies, we have our decomposer, in this case a fungus, that is going to put those nutrients back into the soil so that our grass can get it again. If we would look at this in terms of energy flow, grass would start off at 100%. The grasshopper would be 10% of that energy. The snake would get 1% of that energy. And the hawk will be getting 0.1% of that energy. So only 10% moves on as we can move through our trophic levels. Another important thing to notice when we're writing our food chains is that the arrow always goes in the direction of the energy flow. So the grass, the energy moves from the grass to the grasshopper. If the arrows would be pointing the other direction, it would imply that the grass could eat the grasshopper, and we know that's not true. So make sure that the arrows are always going with the energy flow, or they're always going towards the organism that's doing the eating. Now, a more realistic way to look at how energy flows is through a food web. And just as it entails, it looks like a big web. Food webs are all possible feeding relationships that organisms can have at every trophic level, and they don't always stay the same. This is more natural than what we would normally see with a food chain. We know that we don't always eat the same food source. It changes, and organisms, other animals, are the same way. So here's an example of a food web. We're going to look at the grass down in the lower right hand corner, and notice that we have 3 organisms actually that are going to use that grass as a food source. We have the arrow pointing towards a grasshopper in the direction of the energy flow. We have an arrow going towards a deer, and we have an arrow going towards a rabbit. Now, notice the grasshopper and the rabbit, their only energy source is the grass. Our deer, however, if we look at our food web, shows that it is also getting energy from the tree. So it is using something on that tree for an energy source, probably the leaves. Okay. Notice that tree is also an energy source for the squirrel, and it's also providing food for the bird. So we have multiple ways that organisms can get food, and we have multiple ways that they can be killed. Okay, if you notice, let's look at our squirrel there, and it's getting its food from the trees. Notice it has energy with arrows pointing away from it towards the fox, which would be a predator, towards the owl, and towards what looks like a hawk. So it gives a more realistic portrayal of what it's eating and which trophic level it's going to be in. In terms of trophic levels, we can look at the bird. Notice that it is on the 2nd trophic level when it's getting its food straight from the tree. The tree would be 1 trophic level, the bird would be 2. But if we look at the grasshopper, or it looks like a grasshopper up there, it is eating off of the tree. So that the tree would be trophic level 1, the grasshopper would be trophic level 2, and the bird then would be trophic level 3. It just depends on what that organism is eating at that time. Yep. So, I'm almost done. Do you want to play with your iPad? With the iPad? Or do you want to play with my phone? You know what? I can hook on. None. I can hook onto the internet, which means you can play your Smurf. Can you play Smurfs on here without the internet? Sorry. The third model that ecologists use to show how energy flows are called energy pyramids. Now we have a couple different energy pyramids that we're going to talk about, and they all kind of show this similar information, and they all follow that rule of 10% moving on to the next trophic level. So this first one that we're going to have, we can make our energy pyramid, and we can base it on the energy that's there. Either, grass would be 100%, grasshoppers would have 10%, birds to 1%, and hawks up to 0.1%. We can also look at it based on how much living material there is, or the biomass, how much living material there is. So what is the total amount of grass that there is in terms of weight? How much do all of the grasshoppers weigh? And we should see that same pyramid shape. We can also look at numbers. What is the population of the grass? What is the population of the grasshoppers? And once again, we should see that standard pyramid shape. In this case, we have a energy pyramid. Okay, our primary producer, either a grass usually or some kind of autotroph, is going to contain 100% of the energy. A primary consumer, some type of herbivore, probably gets 10% of that. A secondary consumer, either a omnivore or a carnivore, usually is up at secondary, is at 1%. And then those big carnivores, those top of the food chain organisms, up there at the third level consumer. Now, we would never want to see an inverted pyramid. It would never want to be flipped around, because if we didn't have if we didn't have enough grass to support the grasshoppers, then our pyramid is going to tumble over. And we can see that better here with biomass, or in the next one with the pyramid. Remember, our biomass pyramids, we're looking at the total amount of living matter. So we're looking at some type of autotroph down there at the bottom. And then we're going to follow that same rule of 10%, moving our way up the pyramid. So grass, and then the primary consumer could be a small herbivore like a rabbit, followed by a secondary consumer up at that 500 gram level of, say, like a fox. And then up at the very top, we would have a wolf. We see that same 10% moving on. Okay. The last one that we're going to look at is based on another way of looking at total mass. We could also have this as, that would just say numbers on it. We have more producers than we do first order consumers. We have more first order consumers than we do second order consumers. And if we would see an inverted triangle, this is a good one to look at, where we had very small numbers of producers and we had larger numbers of herbivores and even larger numbers of carnivores, that wouldn't be a very stable ecosystem, because our middle section, that first order consumers, there would be more of them than there would be of grass, and they wouldn't have a food source, so they would have to die off. So you always, always, always have to have a bigger base, and you work your way up like a pyramid, moving 10% of the material, whether it's energy, it's biomass, it's population numbers, and you move 10% on to the next level till you get to that nice pyramid shape. Okay. This is the end of section 2.2. We talked about how our autotrophs are going to be at the base. They're always at the start of our food chain, and that they have to use the sun for to get their starting energy. We talked about our 4 different types of heterotrophs: our herbivores, our carnivores, our omnivores, and our detrivores. We also talked about the difference between a detrivore and a decomposer. So when we talk about our 3 big sections, or our 3 big categories of organisms, we want to make sure we remember that that's an autotroph, a heterotroph, and that third category is actually a decomposer. And we talked about how we can make our food chains and our food webs, and each organism in that is a trophic level, It's that step in our food chain. Our arrows always go towards with the energy or who's doing the eating. And then lastly, we talked about our ecological models, our food chains, our food webs, and our pyramids in showing us just different visual representations of how energy moves through the ecosystems.